All right, hello, welcome to another Zig video where I will show you how to define a sort of a generic type in Zig where you can use one type to pass in several different underlying implementations, let's say. So sort of like inheritance or interfaces, type classes, anything like that. So what problem does this solve? Well, let's say you have a game where you have several different types of scenes that you want to use, and each scene has widely different like update functions. So what you could do is you can create either there's a lot of ways to do it. I'm going to show two different ways of doing this. So first I'm going to show tag union, which is rather simple actually. So it's basically just, let's say you have a TU for tag union, and that's not a convention, by the way, it's just to demonstrate here. And this is how you define a tag union. And then you have different tags. So not dot, you have initial, and this is going to be of type initial scene. And this is just the name of the tag, which can be anything. And in this case, initial, since I'm calling this initial scene. And then I have also some other scene here. All right, so I have two different types or tags here. And the tagged union can be either one of these types. You can add as many types as you want, but it can only be one of these types when you have like an instance of this tag union. So you would have, for example, if let's say I have some other scene here, and this is now a TU scene, and I have to either choose some other or initial here. And I choose this, and then I will just initialize it like this, since it's it doesn't take any parameters or anything. So that's now we have a TU scene type, which contains a some other type. And what we can do with this now is, let's say we have a function called update TU scene, and we take in a scene, which is a TU scene, return void. And then we can say scene, and oops, how do we use this? Okay, so what we do to differentiate this is we do a switch, and we say we have to dereference the scene here. And now we can actually define the different cases that the scene can be. The tag union has two different tags, so it can be either initial or some other. If it's an initial, then we get into this clause, this case clause here, and we say we can actually capture the initial scene out like this. So we capture the inner sort of type there, and we can just call update on that. And I'm just gonna specify these parameters real quick here. All right, so now we have a switch and on the tagged union, and we say if it's this tag, then we get in here and get the initial scene type. Now we can add another case where it's some other, and we can basically just copy this over. So now we have some other as well, and then we don't have any other types that we can have. But now we have a function that we can basically pass in kind of like a generic or base type that can represent different underlying types. All right, so that's basically it for tagged unions. We can talk a little bit about the pros and cons about this. You can see here that for each scene that you have to add it to this list. And then you also have to add it to this list of basically mapping the update function. So that's kind of one of the downsides with tagged union. And but one upside is that it's really easy to implement, and you just have to add it into these two places, and then you're done. Well, actually, there's one other downside as well. It's that you have to know in advance what scenes exists and put it into this list. So that's also one of the downsides. Now, for interfaces, this is a bit more involved actually. So I'm going to show you how to define these and sort of explain along the way on how this works. So I'm going to follow how the standard library uses the same kind of comp time functionality for interfaces. There's probably a lot of other ways you can do it, but I'm just going to follow how the standard library does it for the allocators. And the way they do it is you have first a struct, which is the actual interface itself. And again, the I here is not really convention. I'm just doing it for demonstrational purposes. This time we have a struct. And we have two different things in here. So we have a pointer to the underlying type. So this would be the actual implementation of the interface. And the way we have to define this is we have to say pointer to any opaque. Now, any opaque, what is that? That is anything. It can be any type of any size or anything it can be. And it has to be a pointer here since structs doesn't allow any opaque like this, because then the struct doesn't have a comp time node size, and which it has to have. So we have to have a pointer. Then you have a vtable, and the vtable is basically a collection of what functions that the interface is going to implement. So this is going to be a pointer to a vtable, which we haven't implemented yet, but this is going to be of a iscene vtable type. Now let's define that here. Okay, so the iscene vtable is going to have one field, which is called update. And that corresponds to the function that we're going to map, basically. So the type here is going to be pointer to a const of a function. And the function, the first argument is going to be the context or the actual pointer to the underlying type. And then the other parameters is going to be whatever you want the update function to have as parameters. And in this case, I have a delta time of f32 and I have an absolute time here of f64. And then it returns a void. So that's basically the vtable. Now, the interface can contain some convenience things. So, for example, we could add a update directly here, which calls the update of the vtable. So we basically take in an iscene and we take in the parameters that's needed for the update function. And now we call update on the vtable. And in here, we have to pass in the pointer. And then we just pass in the other parameters. All right, so that's a convenience method. So if you have something of type iscene, you can just call update on it directly now. So another thing that you can do to kind of make this more convenient as well is that you can have an init function in the iscene to actually pass in the implementation type, and it will construct an iscene for you. So let's define this function. And you can see here that I actually say any type in this case, and I'm going to show you why. But yeah, in here, we need to return an iscene. And the pointer is going to be the pointer. And the vtable. And what is update? Well, I'm going to pretend that I have a type that I can say grab the update from. We don't have this type yet, but we can get the type. Now, to get the actual type, we want to get the type of this pointer. However, since the pointer is an pointer, we actually have to grab the inner type of this pointer. And we can do that by using type info like this. And we also have to use type of pointer. Now, to actually get to the pointer type, we have to make a switch here. And we have to check if this is a pointer. And now we can reach into the pointer type and grab the child, which is a type. So this is the underlying type of the implementation. And if we get anything else, then we can throw a compiler error. Now we have an init function, and it can contain any type, but the type itself actually has to conform to some sort of constraints, which is in here, we check the type of the pointer is going to be a pointer. If it's not a pointer, we throw an error. And this is all happening in compile time. Then we actually get the type out here, and we say that this has to contain an update function. And it also has to conform to this update type as well. Because if it doesn't, then this line is going to throw a compile error as well, because the signatures of the functions don't match. So now we are actually ready to define one of these scenes. So the first thing that we need is the underlying implementation. And it's going to be of type some other scene. Now, we also need to wrap this in the iScene by calling the init function. All right, so now we actually have an iScene value, or a value of type iScene. And let's say that we have this function update iScene. And now in here, we can just say scene.update. Yeah, that's basically it for scenes. And let me also show you what happens if you try to do something bad here. So and now you can see that we get some sort of compiler here. And it says pointer to IC vtable does not support struct initialization syntax. And this is because vtable is actually a pointer. And this is how it's implemented in the allocator struct. And the reason is that you only have one of these values that you pass around, and you pass the pointer around. So you have to predefine the vtable basically. In this case, I'm just going to say like this, and it will not work. Check the type pointer to any opaque, found pointer to some other scene. Oh, it's because this is const, so this has to be a var. Okay, now we get, all right, this has to be address. And this also has to be a var. And there we go. So with a little bit of fiddling around, we got the compiler to disappear. Okay, and this is basically what you need for the interface. Now, I'm going to show you what happens if you pass in something else here, because the init function, if you remember, takes in any type. And what happens if you can pass in anything in here? What happens if you pass in like a number? And you can see that we actually get an error here in compile time, and it says that this needs to be a pointer. All right, so this needs to be a pointer. So let's, what happens if we construct like a fake scene here? And you can see here that, well, yeah, it comes, it is actually a pointer, but down here it says that, yeah, this struct doesn't have a member called update. So you will get the compile time error here instead, complaining that this doesn't really implement the interface, basically is what it's saying. And yeah, so you basically have these sort of constraints that you can have on this interface. And you can actually have like any sort of arbitrary constraint that you want that the SIG type system supports. you can look into the type, and with the type info, you can look at all the fields, you can look at the declarations, and you can do a whole bunch of stuff with this. But this is a basic example of how the interface could be implemented. And you can pass in here any type of thing that actually implements the update function. So yeah, if we go through a bit of pros and cons for interfaces, well, you can see if we compare, the tag union is way more simple to implement, except if you have maybe like 100 different scenes or whatever. Then this becomes a lot more cumbersome, because the interface, this is all you have to do with the interface. You don't, for each new type, you can just construct it and you pass it into this init function and it will just work. So that's one pro of the interface. You don't have to bookkeep all the different scenes. But a downside with the interface is that you have a pointer here that you have to dereference every time you want to access this scene. Every time you call update, you have to dereference this pointer. And maybe this isn't the issue in this case, since scenes, this only happens like one times a frame. But it could become an issue if you start to use it with things that are like in massive amounts of entities that has all these pointers that you need to go into. That might become a performance issue. So yeah, that's gonna be it for this video. I hope that I've teach you something about these types that you can make in Zig. And have a nice day, and I'll see you next time. Thanks for watching. Bye.